Hi guys, welcome to today's recording. In this video, we'll be going through the 2021 NCEA Level 3 3.4 examination. So let's just get into it. And if you've been struggling with this particular topic, make sure you check out my other videos as well. You know, there's certain concept videos or older examination videos, and sometimes I will probably live stream again before the end of the year to go through some of your questions. So let's get started. So first one, complete the following table. So I put the periodic table on the right hand side. So with the electron configuration, you're just making sure you know how many electrons that we're dealing with. So for scandium here is 21 electrons. So what you want to do, you want to make sure that you put in the you write in the correct order. So it's 1s2, 2s2, 2p6, 3s2, 3p6, that's 4s2, 3d1, and that should be 21. So if you add up those numbers, that's 21 electrons. For gallium is over here, 31 electrons. Now I'm going to be a little bit lazy. I can't be bothered writing all of the 1s2, 2s2 stuff, so I'm going to replace them with argon, which is equivalent to this stuff over here. So this bit that I'm highlighting right now, this is equivalent to argon. So you'll be perfectly fine doing these without without writing the full thing. Just write AR, that will be perfectly fine. So that's 18, this is 20, 3d10 is the next one, that's 30, and then 4p1, and that's for 31 electrons. All right, for Fe3+, Fe3+ is here. Fe's, now this is what I would recommend you to do. So Fe is 26, and I would just do Fe first. So it will be argon, and then 4s2, 3d6. Okay, now the reason why it's highly recommended for you to do Fe first is I don't want you to go into Fe3+ and go, oh, that's 23 electrons, because that's 26 minus 3, and that give me 23, and I just do 23 electrons. If you did it that way, you would have got argon 4s2 3d3, and if you did it like that, then this is wrong, because that's not the correct order. So what you need to understand is that you need to do the Fe first, and then you need to eliminate 3 electrons. So remember, when we're adding electrons, the 4s is added before 3d, but when we're removing electrons, you remove the 4s also before 3d. So you're going to take away 3 electrons, we're going to minus 3 electrons, so we're going to get rid of these 2, and then we're going to get rid of one of those and turn that into 5. So this will be argon, 4s, so 3d5. Okay, so simple achieved questions. Like I mentioned in my other videos, a lot of my excellent students just bypass this because it's only achieved. All right, next one, Lewis structure. So same thing. So for SCF4 and ClF4-, for these Lewis diagrams, you need to look at the periodic table and actually look at how many electrons you're dealing with. For SC is over here, Cl is over here, F is over here. So you just add up the number of valence electrons that we're dealing with. So for SCF4, so SC is in group 16. So this is 6 plus 7 times 4. So 7 means there's 7 from fluorine, and there are 4 of them. So this is 34 electrons. For ClF4-, there's 7 times 5, because Cl's and F's are all 5 or 7s. Plus 1, because minus 1 means plus 1 more electron, so that's 36 electrons. So what you need to do is just SCF4, put the 4 fluorines, 1 up, down, left, right, and then just single bond all of them, because your fluorine never double bonds, and then do 8 electrons around each of those fluorines, and if you count those, that will be 4, 8, 32. I need 34 electrons. That's why your SC will have 2 more electrons around them. For ClF4-, same thing. ClF, so do that first, and just always single bond everything, and you do the 8 electrons around the fluorines first, and then you just count, and then you make up the part that you don't have in the middle. So that's 4, 8, 32. We need 36, so that's 1, 33, 34, 35, 36. Okay, so this is a seesaw shape because it has 5 regions 4 bonded, a seesaw. This has 6 regions 4 bonded, so this is square planar. Okay, so and this just in, you know, if you have those study guides or what's the other textbook called, I can't even remember, they have really good explanation of the shapes, so you can have a look at those. All right, now both the vaporization and fusion are positive, and why vaporization is more positive. So this is a typical merit-ish type of question. The reason for the vaporization, you need to understand vaporization is going from a liquid to a gas. Enthalpy of fusion is going from solid to a liquid. So liquid to gas, you're breaking all intermolecular forces, and then for solid to liquid, you've broken some intermolecular forces. So obviously it requires more energy to do this. Okay, so here's the answers. You can have a look. So fusion requires, you know, well, like I said, you're only breaking part of it, and whereas vaporization breaking all of it. So this is a very typical merit-ish type of question. Comes up every now and then. Nothing really special here. Okay, so next one. Potassium nitrate readily dissolves in water. So this is when you see the word now. When you see the word readily dissolves, this means this reaction is spontaneous. Okay, spontaneous, and this is something that you just need to get into the habit of seeing. Not just in 3.4 but also in 3.6 when we later on deal with aqueous, because spontaneity and readily dissolved, you know, this is just what it means. Okay, now justify in terms of entropy change of the system and the surroundings. So if you grinded some exam papers, you would see this quite often, and they even told you the reaction is spontaneous because that's what readily dissolves tells us. So what you need to look at is that you need to look at the system. So that's looking at the equation. Okay, so this is looking at the equation, and you're going from 1 mole. If you look at the left hand side, you're going from 1 mole of solid into 2 moles. So you're going from 1 mole of solid to 2 moles of aqueous. So obviously this would increase in entropy. All right, because this is this is more random as a result. More random. This results in more random arrangement. Excuse my handwriting. Writing on tablet is very hard. It results in more random arrangement. So there's an increase in entropy. Okay, so in the system, the entropy increases. Now look, if you look at the surrounding is that as this reaction takes place, it's either going to absorb heat or release heat. So this is where you look at this part. Okay, so for this part, because this is a positive enthalpy change, that means this is endothermic. If it's endothermic, that means it's absorbing heat from the surrounding, absorbing heat. Okay, if that's absorbing heat, so that means when we look at the surrounding, we're talking about the particles on the outside of the environment. If they are losing the heat energy because the chemicals are sucking it in, if they lose energy, so the air particles or the surrounding particles lose energy, they lose kinetic energy, therefore they're less random because they're not going to move around as much, and that means the entropy will decrease. The entropy, I can tell I haven't made videos for a while. Entropy decreases. Okay, so the entropy of the system increases, the entropy of the surrounding increases. So why is this reaction spontaneous? That means the entropy increase of the system is big enough to compensate for the entropy decrease of the surrounding. Okay, so that's pretty much it. So we're looking at the effect. We're looking at the effect of this being greater than the effect of that. That's why it's spontaneous. Okay, so that's pretty much what you need to do to explain it. And here's the answers. So as you can see, the first paragraph is explaining about the system. So as you can see, you're going from, you know, ions. You're producing ions from solids. greater dispersal, more randomness, more disorder, higher entropy. Okay, so and then the other one, energy is absorbed, so there's a decrease in the air particles energy because therefore entropy decreases. So we know it's spontaneous. The only reason for that to be spontaneous is that the entropy of the system must be greater than the entropy of the surrounding. Boom, excellent question. Very nice and easy. Very, very typical type of question. Moving on. All right, so next one is a calculation question, and when I see this number, this just means it's Q equals MC delta T time. I don't even need to read the rest of the question to know it's Q equals MC delta T, because they gave you C in this constant of 4.18 joules per gram per degree Celsius. All right, so we're dissolving solid potassium nitrate. This temperature decreases, and then we dissolve this amount, assume the mass is 135, so that means the solution is 135 grams, so it's going to be 135 times 4.18 times 21.3, oops, wrong way, because we use final minus the initial, 14.2 minus 21.3, and that's going to give us 4,000. Negative 4,007 joules, which is negative 4.007 kilojoules, and then we use that delta H to equals negative Q divided by the mole to find the enthalpy per mole. We know the we need to find how many moles we have, so calculate the mass for the increase 135 joules. Okay, so how many moles are we dealing with here? Let's have a look. So the mole is going to be, let me grab my calculator. Wait, do I have to, oh wait, I need to use some of the I need to use some of the stuff here. Sneaky. I was wondering why I'm missing clues. So if you come back to first part of the question, they actually gave me the enthalpy. So the enthalpy is 34.9. Cheeky. These guys are getting good at these. Okay, so we know this is 34.9 from the question above I just showed you. This is positive 34.9. We know Q equals negative 4.007, so that means mole equal this N equals negative Q divided by mole. Just rearranging equation again. If you're not good at math, go to Mr. Infinity plus 1, please. Divided by 34.9, and that's going to give us 0.115 mole. If we know how many moles we have, if we know the molar mass, you will know the mass. So M equals N times big M. It's going to be 0.115 multiplied by 101. That's going to give us 11.6 grams. Three significant figures. Okay, so I would assume this is an excellent question. I personally don't like it how they give the question. They give the clue to well, one of the most important clue in the part A, and then they didn't mention it in the part B. That's kind of a you know, not very nice, but it is what it is. All right, next part. Just gonna chuck the answers down. Go down a little bit. All right. Explain the difference between atomic radius on calcium and selenium. So if you look at calcium, let's find the periodic table. Actually, let's paste it in here. There it is. So calcium is over, where's my highlighter? Calcium is over, where the hell are you? Here. Selenium is over here. So they ask you to compare the radius, and then you just need to remember as atomic radius increase, as you go from left to right, the atomic radius decreases. Why does it decrease? Because the number of protons increases. So when you go from left to right, the number of proton increases. So this is important. You need to talk about both things. The protons increases. So there is a stronger, what does that mean? So it means it's a stronger pull or stronger nuclear charge coming from the nucleus because there are more protons. And then the electrons are in the valence electrons. The the valence electrons are in the same energy level. So that means they same energy level, so that means they have similar amount of shielding. And when they have similar amount of shielding but then stronger pull, that means it's going to be pulled in closer, therefore a smaller radius. Okay, so here's the answers. So same energy level, same repulsion, same shielding, number of proton increases, electron attraction. Yeah, you know, just work on the wording. You know, it's my job here is for you to understand, not you know, you need to perfect your answers by comparing yours to the model answers. Okay, and justify with reference to the factors affecting periodic table trends why fluorine is the most electronegative element in group 17. So this is actually something that's quite good to, if you didn't know this, it's actually really good to remember that fluorine, which is sitting on the top right hand side corner, this is the most electronegative, so that means going this way increases, going this way decreases. So it's a really handy element to remember. So why is that, you know, why is that very electronegative? Because it's a, I mean, if you think about it, it has 9, it's sitting right up here. If you look at the periodic table, so this, when you're going down, like say, what, you know, we kind of explained half of it already. When you're going this way, the atomic radius decreases. So fluorine is a very small atom. So fluorine is really small. Okay, so it's the smallest atom, you know, and then it has a valence electrons very close to the nucleus. So, you know, that's why they have a stronger force of attraction, because they have so much more force of attraction come from the nucleus, because they have the lowest amount of shielding effect, they have the least amount of repulsion, because they have just, you know, just the right balance to give you the most amount of attraction force. Okay, so if you look at that bit here, so going up the group, so, you know, at the top of the group, because so the number energy level decreases, so there's at least the shielding, I mean, going up a group, let's see what it says here, the number of energy level decreases. Going up a group, the number of energy level decreases. Yeah, of course. So as does the repulsion. Yeah, because there's you know, there's less. If you think about it, if you do 2-7, not the best way, but, you know, coming from year 11s, year 12s, you know this. Like say if you have 2-7 versus 2-7, you have fluorine versus chlorine. As you go up the group, the number of energy level decreases. You're going from, you know, this is 2 energy levels, this is 3 energy levels. So the repulsion, so obviously fluorine has the least amount of repulsion and the least amount of shielding. So there has less shielding, less repulsion, and that means it can, the protons have a stronger pull on the valence electrons. Okay, so, or on the bonding electrons, because we're dealing with the electronegativity. Okay, all right, calculations. Oops, on there too quickly. So this is oh, this looks like a Hess's law question. So this is like a simultaneous equation here. So let's have a look at this. So this is our, remember when you're doing Hess's law, I do have a video on this. You can have a look at that. So this is the goal that we're trying to get to. Like we're trying to rearrange these equations to become the one that we have on top. So what we're trying to do, we're trying to have 4 NH3. So as you can clearly see, this is the only one that has NH3. So I'm going to multiply the first one by 2. And then I need, now you can see this O2, there's O2 here, there's O2 here, so don't do that one, do that one, do that one at the end. Now we need 4 NOs, nitrogen oxide, which is right there. This is the only one that has NO, so I'm going to get number 3 to multiply by 2 to give me the 4 NO from 2 NO, and then 6 water. I need 6 water on the right hand side. I only have 2 water on the left hand side, so that means I'm going to reverse, well, I'm going to reverse, I can just do, I'm going to do number 2 multiplied by -3. You know, that would help. So number wise, this is going to be 92 times 2, this is going to be 180 times 2, this is going to be -3 times 572. Oops, 572. Now I'm not even gonna bother writing out the whole thing because there's literally no point. I mean, you can, you know, if you want to prove yourself that you did it correctly, what you can do is that, you know, when you multiply by 2, you can do 4 NH3 plus turning into 2 N2 plus 6 H2. You know, it's recommended that you do this, and so this is, and then you can write the other 2 equations, and you can start crossing them out and go, yay, look, I got the correct answer, but I'm just gonna shortcut it here. So add up these 3 numbers, and this is gonna be -1172 kilojoules per mole. And you know how we chemists, NCEA chemists, are obsessed with 3SF, so make sure you round to 3SF, please. Okay, very nice and simple, Hess's law. Next one, explain why the standard enthalpy change calculated in part I will be more exothermic if the water is produced as a liquid. Okay, so we're dealing with a gas here, so obviously will be more exothermic if the water was produced as a liquid, because you need to get more energy. Well, actually, sorry, you need to release more energy. One is turned into a gas, one is turned into a liquid, so you need to, you know, producing liquid is, you tend to release more energy because you are forming more intermolecular forces between the water molecules, because you want them as a liquid. I'm not sure if that, you know, because if you think about it, gas has the least amount of intermolecular force, liquid has more intermolecular force compared to your gases, so you got to release more energy in order for this for this process to happen. So there we go. So the enthalpy will be more exothermic because the heat energy will be released, yeah, because, you know, there's more intermolecular force. All right, that's a very short answer. Anyhow, next one, question 3. How are we going with time? Actually doing pretty well. Question 3. Now, this is butanol. So attractive force on all of these, let's just double check. Yeah, all of them, you can do this first. All of them have temporary dipole to dipole attraction. Okay, because they're all in molecular solids. Okay, they all have temporary dipole-dipole. Now this is permanent. This is polar, so this also has permanent dipole-dipole. This is hydrogen bonding right here, so this also has permanent dipole-dipole, as well as hydrogen bonding. Now, so, and then they just talk about, right, justify the difference in the standard enthalpy. Okay, so they want you to talk about why this has the highest, pentanoic acid has the highest boiling point compared to propanoic acid compared to butanol. Okay, so you want to first of all talk about their, you can, you know, just compare them roughly. Like say, for example, if you look at butanol and propanoic acid, if you reverse these two together, they roughly have the same molar mass, because remember, temporary dipole-dipole force of attraction is dependent on the molar mass. So if the molar mass is similar, then you look at the other things, because you can have a non-polar molecule, but it's super big, having a higher boiling point and melting point compared to a molecule that has all 3 intermolecular forces, just because of the temporary dipole-dipole force of attraction being so big, because the mass is so big, making the molecule a lot more polarizable. So in this case, if you look at butanol, their temporary dipole-dipole force of attraction will be similar, but because it has hydrogen bonding, that means it's going to take more force of attraction to break. Okay, and then if you look at propanoic acid and pentanoic acid, they both have hydrogen bonding and permanent dipole-dipole force of attraction, but the pentanoic acid is bigger because this has 5 carbons, this has 3 carbons, so straight away this has a larger molar mass. This has a larger molar mass, which means you are going to have a stronger temporary dipole-dipole force of attraction, which means it's going to require more energy. Okay, so as you can see, you know, similar to the way I did it, so similar size. So similar temperature dipole force attraction. They both have permanent dipole, but then the other one has hydrogen bonding, which means, you know, blah 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 blah, more heat energy is required. The other one, they both have hydrogen bonding, they have similar sort of stuff, but then one is a lot bigger, so stronger temperature dipole force attraction due to a larger molar mass. So this is a very, very typical question. All right, next one. So what are we dealing here? Write the equation for the enthalpy change equal to the standard enthalpy of formation. So formation is you're forming this from the constituent elements. So we are dealing with oxygens and hydrogens. So 6, 6, 3. Okay. So this is gas. This is gas. Actually, since when did carbon become gas? This is a solid, this is a gas, this is a gas, and this is a solid. Now, just do one bit extra. You know, this is the enthalpy of formation. Here's a test for you. Can you do the enthalpy combustion equation? So combustion, you could pause the video here, but if you want the answer here, it's going to burn in oxygen, it's going to produce CO2 and water, and then you combine, you balance it. 6, 6, that's 12, that's 18, 18, there you go, that's 18 electrons, sorry, 18 electrons, 18 oxygens. Okay, so that's balancing, this is enthalpy of combustion. All right, next one here. So glucose is oxide, blah blah blah. So we got this. So what do we know? So we know the enthalpy change, we know the enthalpy formation. Okay, so this is a typical when you see the products being given, the formation being given, and then you know this, and they ask you to find the formation for this. This is a typical products minus reactants kind of reaction. So you just need to remember enthalpy change equals the enthalpy formation of the products minus the enthalpy formation of the reactants. So we know this delta H is negative 2803. The products is this, I don't know. So let's make it X. X plus 602, 6 times 0 is 0, so not interested, minus products 6 times CO2, which is negative 394, plus 6 times negative 286. So that's gonna be so this is gonna be negative 2803 equals X minus, so inside the bracket is going to be, bear with me, I'm just doing this on my calculator. This is negative 4080. So X, so X equals negative 1277 kilojoules moles per liter. And because again we are obsessed with 3SF, so this is negative 1280 kilojoules per mole. Voila, done. Okay, so just remember, when you see enthalpy formations, add up the products minus reactants. That gives you the enthalpy of change. I believe this is the last question. Yes, it is. So this is looking at the shape and polarity. So this shape is octahedral. So you know, identify, explain the shape. So I normally talk about the shape first. If they specifically, actually in this case, since they're asking about polarity, always remember, ever since if you watch my video when you're year 12, I always talk about the polarity. It comes from two parts. One is from the bonding, so you need to talk about the bond dipoles, and then one you need to talk about the shape and symmetry, and then you talk about them together. Okay, so bonding is looking at the bond dipole formation, so you can't just say, oh, the dipoles cancel each other out without even telling me what dipoles we're looking at. Okay, so we're looking at here, there are two types of bond here, so we've got SCl and SF. So you can say that the SCl and SF bonds are both polar due to significant electronegativity between the atoms that are bonded. So these are polar covalent bonds. Now, and then this has 6 regions of electron density, and they are all connected, they're all bonded. So this is going to give us, they're all bonded. This is, and then we take positions to minimize repulsion. So this is going to give us an octahedral shape. And then, so this is symmetrical, but even though it is symmetrical, you got different strength of bond dipoles, different bond dipoles, so they're not gonna cancel out equally because atoms are different. So therefore this is polar. Okay, so here we go. So the bond, so you need to tell us talk with the bonding. So this, you can just say these are polar covalent. You don't need to tell us which one's more electronegative. I mean, you can tell from the periodic table trend, and then you can tell us the shape and the symmetrical shape, the symmetrical arrangement. But the dipoles, they have different strength because they're different atoms. So the different atoms have different electronegativity. So therefore, this is a polar molecule. Okay, and that's that. All right. So hopefully this is helpful enough. So do check out my other videos if you you know, need more assistance, but I will definitely grind out all of the 2021 examinations before the school examinations in term 3. All right, so hopefully this has been helpful. So leave a like, subscribe if you haven't, and I'll see you guys next time. Bye bye.